75.
Right.
Thank you. And I'll turn this in next week.
This is a data set on the people on U.S. senators. There's 100 U.S. senators right now who are in office, so it's a population of senators. Oh, here it is. See here, see all this information I have? Gender, political party, the number of colleges each person attended, the years in office, number of years left in office, age, total number of degrees earned. So this is a population of all 100 senators. Oh yeah, and then in sheet 2, notice how we only have 30 senators out of the 100. So this is a sample data set. It's a sample of 30 out of the 100. And then over here, it's a smaller sample size of 10. Let's see, this is only 10 out of the 100. And I selected both of these samples randomly. What I did was I went to a computer program called a random number generator, and I said, give me 30 random numbers out of 100, and then that told me which people to pick to be the sample. So what if we calculated the average number of colleges attended? That's the first column. We could go up to formulas up here, go to more functions. This is if you're using Excel 2013 or 2010, I think. It says statistical right there. This is average, so it calls mean average. Now I have to highlight this entire column. Going all the way down. And before I did that, before I actually highlighted, I had to make sure an empty box was highlighted so it has a place to go into. Make sure it'll cause a problem if you do this and you're actually highlighting what you're actually up here somewhere, because then it'll try to put your answer into one of your data cells. So you have to have an empty box. So this is a population, this is our first population mean, because it's the mean of a population. Now what if we wanted a population standard deviation? Standard deviation of the number of degrees earned. We would go up here again, statistical.
Yeah.
These are all in alphabetical order. See where it says STDEVA and STDEVP? Population means population standard deviation, meaning it's not dropping the number down by 1. We're going to use that because we're dealing with the whole population, right? It's all 100 senators. I mean, no population members are missing. So now let's highlight this. The population standard deviation is it's 0.719. Now let's go up here and see which other ones can we do this with? You can't get a mean and standard deviation for gender and political party because it's not numbers. But we can do it for all of these other ones going to the right. If you click down here at the bottom right corner, we can drag this across. Did you see me do that last time? Those are all of the population means. All of the standard deviations right here. So how many do we have? We have 1, 2, 3, 4, 5 means, right? And 5 standard deviations. 4, 5. So remember the word population parameter? All 10 of these would be population parameters because they're all population values. So we have 5 population means, 5 population standard deviations, and all 10 of them are population parameters. Now let's do the same thing with our samples. First, that's a sample size of 30. These are all going to be sample means, starting with colleges attended. For average, we just go to average again because a sample mean and a population mean are they're both just averages. But now, what about sample standard deviation? What are we going to do now? Now we have to go up here to more functions, statistical, and we have to go down to STDEVA, which is for sample standard deviation. So now we're using this because it's not a population anymore, it's a sample standard deviation. Oh, I didn't highlight them. So 5 sample means, 5 sample standard deviations. All 10 of them would be called sample statistics. That's the word for a sample value. So we have population parameters and sample statistics. Let's do it for our sample size. This is our sample size of 10. So it's going to be STDEVA again, because it's still a sample. Now I said that since I selected the samples randomly, I did random sampling, the sample means should be close to the population mean. So the population mean for number of colleges attended is 1.77. The average senator goes to this many colleges. Let's see what the mean of 30 came out to for colleges. Came out to 1.63. So it estimated it pretty close, right? 1.63 is pretty close to 1.77. And now we can check our smaller sample size of 10. Remember, a smaller sample size should have less accuracy, even if it's random. So 1.6. So for colleges attended by senators, population mean is 1.77. Sample mean of 30, or at least the 30 that I chose, was 1.60. 1.63. And sample mean of 10. .6. So the sample of 30 and the sample of 10 both did about the same accuracy. I mean, these two were about not that far off from each other, but the sample of 10 was a little bit less accurate. Because this 1.6 is a little bit further from the population mean compared to this.
How come with the standard deviation there's more of a difference between the three sets than the mean is?
Oh, you mean
What's
in
causing
here?
that? Yeah, what would be the cause of that?
So the sample size of 10 was 0.516. This was 0.66 and 0.719. I don't think anything's causing it. I think it might just have to do with chance. Sometimes when you're taking random samples, they vary a lot just because of chance. So if we redid this with another sample of 30, it might not happen again. And if I threw out my sample of 30 and I randomly selected 30 again, I'm not going to get the same number twice, right? Probably. Because if I select a different group of 30 people, it's a different group of people.
Okay.
So they're not going to have the same average, probably. So if I happen to get the same 30 people, then of course it's going to be the same. But if it's a different group of 30 people, then a different group will have a different average.
Professor, I have a question. So in the future, for the future assignments, would you like us to, like, how many decimals would you like us to round up the
values?
Yes.
Usually I have you round the values to the nearest, to 1 decimal place.
Mm.
So the nearest 10th.
Right. Thank you.
That's fine.
Yeah.
So the difference between statistic and parameter makes sense. The 10 values that I calculated with the whole population down here are all parameters, or population parameters. All of the values that I calculated with samples would all be called samples. They're called sample statistics. And also notice that these values, like mean and standard deviation, they only describe one column of data. So you see how this mean and this standard deviation summarizes only one column of data, and then this column has its own mean and standard deviation. So every column has its own mean and its own standard deviation all the way across. That's why sometimes they call them one variable statistics, because they're just one summarize. They're only dealing with, they're only calculated with one column of data, meaning one variable. So next we'll talk about we'll still be talking about how to describe one column of data, but now we'll talk about how to do it with charts and tables. That's where we get into histograms and frequency tables and histograms. So a column of nominal data, meaning, see how gender right here? Gender and political party are both called nominal variables. They have categories that don't follow any order. What we would do with these is we would make bar graphs. Like, we could make a bar graph with all of the genders and another bar graph for all the political parties. So if I asked 10 people for their favorite colors, and their answers are red. Well, 2 people say red. 1 person says blue. 3 people say green. Yellow, purple, and no, 2 purples and a brown. It would just be like this. Red. You put all the possible categories down here. We just count how many of each we have. We have 2 reds, so this goes up to 2. We have 1 blue, so it goes to the 1 tick mark. 3 greens, so that's here. Yellow, 1 yellow, 2 purples, 1 brown, like this. It's a bar graph for nominal data. And you would also make a bar graph for ordinal data too, meaning if I was recording grade levels. The only difference with ordinal, with an ordinal variable like grade level, is that you would order the categories down here. So what if I was doing college grade levels, I would go freshman, sophomore, junior, senior in order. But it would still work the same way. So nominal and ordinal data both go with the bar graph. The difference is, with ordinal, you have a certain order on the x-axis. So order of categories on x-axis does matter. With colors, it didn't matter. This was nominal, so it didn't matter which order I put them in. So we'll put this right here. Nominal data, order of categories doesn't matter. This is grade level right here. Does everyone see how I have S, J, F, S, J, and S. It's just freshman, sophomore, junior, senior. This is favorite color. This is grade level. What if this is my data set? F. See how I recorded the grade levels of these people right here? 1, 2, 3, 4, 5, 6 people. We have 3 freshmen, right? So it would be like this. 1 sophomore, 1 junior, and 1 senior. So the rest of it is pretty flat like that. Maybe I should say order of categories on x-axis matters. Because that's what I mean. Can you see that over there?
Yeah.
Here's PowerPoint. Oh, yes?
Will you upload the Excel file onto the doc sharing later?
Yeah, I can.
Thank you.
You're welcome. These are descriptives. This is frequency. One sample. Oh, I can go here. So I'll just get the PowerPoints off of the web. Here we go. I don't have any in-class questions for this PowerPoint, but I do for the second one. This is already what we already talked about. Well, down here, a column of quantitative data can be described with a frequency distribution table or a histogram. So in that spreadsheet that I had when I had the data from the senators, the first two had category answers, gender and political party. The other columns were all quantitative, like number of colleges, age, number of degrees. Each of those columns would be described with a frequency table or a histogram. So we could do that for each of these columns. So we could make a frequency table for this column, another one here, and another one here, and just one for each. So each one of these would have its own frequency table. And first, let's talk about what the word frequency means. It's just the number of times that a value appears. So if I ask 8 people to tell me how many classes they're taking, and these are the 8 answers, frequency, this answer right here, number 2, 2 classes has a frequency of 3, right? 3 classes has a frequency of 2. 4 classes has a frequency of 2, because 1, 2. The answer 5 has a frequency of 1, because there's only one of them in here. So a frequency is just a count. It's just the count of how many times that answer appears. And the frequency table has 2 columns. It has one column at the top that has an X that lists all the different numbers that appeared. And it has a frequency column that lists the frequencies. So let's take a look at an example right here. We're asking 10 people how many times they go to Starbucks per week, and we get these answers. These are just the frequencies. What values appear? There's 1, 2, 3, and 5. And the frequencies of those are 4. There's 4 of these, 2 of these, 3 of these, and 1 of this. So it's like this. The answer 1 shows up 4 times. The answer 2 shows up 2 times. The answer 3 shows up 3 times, and 5 shows up 1 time. And that's, I said we had 10 answers, right? So all of these have to add up to 10. So 4, 6, 9, 10.
So you get the 10 from the 10 people?
Right. Each person has 1 answer.
Okay.
So 10 people means 10 answers. What if we had decimals? If decimals are possible, the simplest way to deal with them is to round them off. That's if you want to just have whole numbers. So if we had if we asked 4 people how old they are, and these were their answers, if they gave a decimal, we could just round them off if we wanted to whole numbers, and then make this table. This rounds to 25, right? This 27. This rounds up to 22, right? And this also rounds up to 23. Whenever this number, right in the decimal places, whenever it's 0 to 4, you round down, 5 to 9, round up. So our answers are now 20, 22, 23. Now we have 22, 23, 25, and 27. But what we have to do when we make the table is, this is our lowest number, right? And this is the highest. We can't skip over any in between. So for 24 and 26, I just put zeros in there. We don't have to include 21 because it's below our lowest value, and we don't have to have 28 because it's above our highest. But the ones in between have to have zeros. You can't just go 24, 26 because, well, it can be misleading to the person who reads the table. And another problem that you might deal with besides just having decimals is sometimes you have too many different answers. If I did some type of telephone survey with random people and I asked people how old they are, I could get lots of different ages because a person could be anywhere, a person answering the phone could be anywhere from 5 to 100 maybe, or maybe even older than 100. So I could get lots of different answers. And if I tried to list out every answer in my left column would go down forever, or it'd be really long. So instead of actually listing every age in the data set, I could just create these groups. Like in my left column, I could have 0 to 9, 10 to 19, 30 to 39. When you do that, each group is called a class interval. So this right here is called a class interval. This is another one right here. Another word that people often use for them is they call them bins. That's kind of a shorter word because it's like a bin of numbers. We asked 15 people how old they are, and we got these answers. All I did next was I created these categories, and I just listed how many people fell into each category. We had 2 20s, we had 6 people in their 30s and 2 people in their 40s. So you see how 30 to 39, it says 6 right there?
Mhm.
That's just because if you go back here, if you count how many 30s there are, you have 1, 2, 3, 4, 5, 6 30s. So that's why 30 to 39 has a 6. And if you count the 20s, you have 1, 2 20s. So 20 to 29 is a 2. So it's a grouped frequency distribution table, just because we have these intervals instead of whole numbers. We have 5 class intervals. Each one of these things is called a class interval. So we have 1, 2, 3, 4, 5 of them. And there's something else called a class width. These are two concepts that are easy to confuse with each other. Class interval and class width. Those are 2 words that I think people mix up a lot on exams. Class width is the number of numbers inside each interval. It's the range of possible values covered by each interval.
So you'd have to keep it consistent?
Right.
The width for all of it?
That's true. So this one you couldn't have 20 to 29 and then 30 to 34 and then 40 to 89 because you have to keep them the same. So class width, class width equals it's actually upper boundary minus lower boundary plus 1. I have to explain what these are. When we have these groups right here, each of these numbers here is called a lower boundary. So 20, 30, and 40 are all called lower boundaries. 29, 39, and 49 are upper boundaries. So let's start by finding the class width of this one right here. 29 minus 20, meaning lower boundary is 29. Upper boundary, no, I mean, lower boundary is 20 plus 1. So it's 29 minus 20 plus 1, which is 9 plus 1 is 10. So each of these class intervals is going to have a class width of 10, right? Because they're all the same. We could do it for every one of these, but we're going to get 10 every time. And some people might get confused about why this is a width of 10, because when you look at 20 and 29, it seems like it should be 9 when you first think about it. But there's actually 10 possible numbers in here, because 20, 21, 22, 23, 24, 29. There's actually 10 numbers in between 20 and 29, and that's why it's a class width of 10. Class width is 10. These are just some guidelines about how to create the intervals. It just says it's used, sometimes it's recommended to use between 6 and 15 class intervals. I can't remember how many we used, but we only had 5. So we weren't following the guidelines, actually. The class width should just be a nice number, like 5 or 10. It's better than having weird-looking intervals like going up by 7 at a time or going up by 3 at a time. Oh, and we talked about this already. All intervals have to have the same width. Like how ours are all 10. Now, you can take a frequency table and make it into a certain type of bar graph called a histogram. All you do is you take each frequency and make it into a bar. So now let's take the table that we had before, which was this one right here, where we go 2, 6. See those numbers, 2, 6, 2, 4, 1? Now we have 2, 6, 2, 4, 1. So it's still just the number of people in the 20s, number in the 30s and 40s, so on. But now it's just every frequency is a bar. So everyone can see how these numbers match the numbers we had in our table, right?
Right.
And when you make a histogram, the bars can actually touch. When you make a nominal bar graph, like we did before with favorite colors, the bars aren't supposed to touch in that type of a bar graph with categories. But in a histogram, they do touch like this. And a histogram can show something called the shape of the data, or have you heard of the shape of a distribution? See how this follows a certain shape right here? It goes up and then down and then up and down again. This shape becomes a lot more obvious when you have a graph than when you have a table. A lot of the time they'll outline the shape with bars like this. You'll see a curve like this. So the curve outlines the shape. And it's called a distribution. Distribution is really just a word for shape, the shape of the data. You know when you're spreading something over a surface, you can say it has a certain distribution. Like if you're trying to paint something, and you can see that the paint is sort of it's sort of going up and down, and it's not really even. Then that would mean that your distribution of paint isn't even like it's supposed to be. So it's sort of like, or you're taking you're taking a knife and you're spreading the data over a surface, and the distribution is just the way it piles up like this. Like if you got a piece of toast like this, and you're spreading something over it, it's like this is your peanut butter distribution, that it follows that shape. So it has kind of a wavy distribution, right? Just like how this has kind of a wavy distribution. Now, here's another frequency table with a graph right here. I'll give them about 5 minutes to do whatever they need to do, and then we'll look at this again.
For the notes, for the extra credit, do we have to write it